So I want to make sure, because we're going to do a close-up view as I demo some of these rules for circuits. But I want to make sure that you get this page out and in front of you. There's two different types of circuits that we can build. So I'll build a couple here in front of you, and that way you can see them first. But if I take and just have a simple circuit like this, and I light this bulb. So if I just have a simple circuit like that built, then if I wanted to add another bulb to that circuit, I can add it one of two ways. I can either give it its own power and ground just like that one, and then we refer to this as parallel. These are parallel branches. This one has power and this one has power in its own ground, and that one has power in its own ground. That's referred to as a parallel circuit, or I can hook them up in one continuous string, like this, which is called series. So I can hook them up and I can build a circuit as a parallel circuit or as a series circuit. And so this is a series circuit, which I know you guys have experienced before, because everybody freaking loves Christmas, and then you've had that long string of Christmas lights that if one of them burns out, then they all go out. So Christmas tree lights are in series. They're wired up in series. So where if you lose one or get a break, since there's only one path through that whole thing, if you break, if one bulb burns out, it kills everything on that whole string. So that's the rules for series and parallel circuits. Get these out and get them in front of you so that as we cover it in this close-up view, I'm going to reference these rules. But for a series circuit, we say current is the same everywhere in the circuit. The sum of all the voltage drops in the circuit equal the source voltage, and then the total resistance equals the sum of all the individual resistances. Parallel circuit, voltage is the same everywhere. The total current is the sum of the current in each branch, and the total resistance is always less than any individual resistance. So we're going to break these down. I'm going to demo each one of these circuits and prove these rules out to you, and then I'm going to zoom in on this for that. So what we have in front of us here is a series circuit, and so the first little rule and law that I want to explain is that for a series circuit, it says that current is the same everywhere. And so conceptually that makes sense if we look and say, well, okay, there's one wire coming out here and it goes and it has to go through the resistance of this bulb and go through the resistance of that bulb, and then it returns back through the other one wire back here to the battery. Okay, yeah, that makes sense. So I also want to just prove it out to you. And so when we measure current with a meter, then we're going to turn our meter over to amps. And so when we turn our meter over to amps, this meter defaults to AC amps. So I'm going to need to switch it to DC by pressing that yellow button there, and then it will say DC amps over here. So then when you measure amps, I have to make sure that the amperage comes and flows into my meter. And so in order to do that, I have to install my meter as part of this circuit. And so in addition to that, I have to make sure that the cavity on the meter matches the setting on the dial. So we never mess with the black lead, that's always stays there. But when I want to measure amps, I have to place it onto amps. And if you're ever on the wrong one, this meter will yell at you. If I'm like, well, I'm going to measure ohms and the lead's in the wrong spot, it'll yell at you. So if I'm on amps, then it's happy. So if I come over here and I measure my amperage and I just clip on that side, over here, and then on that side over there, it'll cooperate with me. So in measuring amps there, so now I got to go back and switch back to DC. So in this case, I'm getting 0.166 of an amp, or 166 milliamps. So, and I'm on the ground side there. So, that is my reading of current for these two bulbs. So then, if I went over and I measured the amperage on the other side, the law says current is the same everywhere. And so if I hook this back up and I go and measure amps on the other side, am I going to get anything different? And you better be saying no, because we're talking science. I don't know if anybody likes making bets against science. It's like making a math bet against like 1 + 1 = 2. So that would be a bad bet. So if I measure the amps on this side, let this guy sit and think about it for a second. About 0.163. I'm going to bet that my resistance changed and I still got it the same over here. .163, .164. We're getting the same amperage on both sides like we expect to get. I want it to come out exactly the same for you guys. .163, .164. So current is the same everywhere. One of the explanations for what's going on and how I'm chasing it is because the bulbs, when they turn on, they warm up. And if I let a bulb go out and I disconnect it, it'll cool off, and then it will, as it cools off, its resistance changes, and so if resistance goes down, then the amperage will go up. As these bulbs sit here and get hot, their resistance is going to increase, and so the amperage flowing will decrease. But one of the things I want to make sure that you see and understand is that in order for this meter to measure the amperage here, if I separate out these wires a little bit where we can see it, then I want you to be able to see that the amperage that's flowing in this circuit is coming in on this black lead here. So it's coming into this black lead through this wire here on red, and it's going into that bulb through this black lead, or into the meter through the black lead, and then out of the meter on the red lead to this bulb. And so ideally, if you can see it on the screen, you'll see that there's a minus there, but I still have the same number, the 0.164. So if I go and I switch my polarity of my leads and make this a little more true, we're still going to get the same number, but the minus will go away. Truthfully, so now the minus is gone off of this lead here, or off of the meter, because now I have my red lead towards the more positive place. But the current that's flowing through that bulb now is now flowing through my meter. So it's coming out through the meter, going in my red lead into the meter here so that the meter can measure it, out the black lead and on to the rest of the circuit there so that the meter can measure it. But current now is the same everywhere in this circuit. And so it's not going to matter where I measure it. If I measure it on the positive side like you saw, or if I measure it on the ground side, or if I measure it right before it gets to the battery, that current, whatever current left the battery on this positive side is going to continue through the rest of the circuit and come back on the ground side, because there's only one path in a series circuit. So hopefully that concept makes sense to you. I also want you to understand that when you're using this meter, we hook our meter up in series with the circuit. Even if we had a parallel circuit here built, we still have to always hook the meter up in series. So the current that's flowing in the circuit has to flow through the meter to measure it. So you always have to take the circuit apart, install your meter in line with that circuit so that that current will flow through your meter so you can measure it. So that's that for current is the same everywhere. Now, the next concept to understand, and the next one that I want you to understand, is going to be the concept of a voltage drop. So I want you to write this down, and it's in some of our other notes, but I find writing stuff down helps me commit stuff to memory. But the definition that I have of a voltage drop, so voltage is electrical pressure, and the definition for a voltage drop is the difference in electrical pressure between 2 points. So what we're saying with that is I could measure the difference in electrical pressure between here and here. I could measure the difference in electrical pressure between here and there, between here and there, between there and there, between there and here, all right? Which is exactly what we're going to do next. So we're going to measure the voltage drop across the circuit, and I want to demonstrate to you what a voltage drop is. And a voltage drop, by definition again, is the difference in electrical pressure between 2 points. So I have just a little diagram that we're going to use to illustrate our voltage drop testing and our difference in electrical pressure between 2 points. And so what we're going to do is we're going to measure the voltage available from the battery, and then we're going to measure the difference in electrical pressure between here and get a reading, between here and get a reading, between there and get a reading, or there and there, sorry, and then between there and there back to the battery and get a reading. And so on here, what that would be is we're going to measure at the battery like this, then we're going to measure our power wire, then we're going to measure this bulb, then we'll measure this bulb, then we'll measure our ground wire. And so the sum of all the voltage drops, this voltage drop plus this one plus this one plus this one, will be the same as the source voltage, all right, or equal to the source voltage. So we're going to go ahead and do that. So to start out, we're going to measure the difference in electrical pressure between here and here on volts. So I'll turn our meter over to volts, and this should work out a little better. So between there, and I'm starting with 12.63. So I'm going to write that down for my first one. 12.63 volts. Then the difference in electrical pressure between there and here. There and there is 0.009 of a volt. Let's see if this helps at all. So I got 0.009. Then the difference in electrical pressure between here and here. So I get 6.40708. There's 40. Come on, be still. $6.413. That stayed pretty still. All right. So then I'm going to measure the difference in electrical pressure between here and here. For my next bulb, 6.200. Close enough. All right. Then the last leg, difference in electrical pressure between here and my battery, 0.008. So if I add all of those up, 6.413, 6.200, 0.008, 0.009, and I add those up. Oh my God. Nice. Worked out perfect. So when I add all of that up, then add up my voltages there, it adds right back up to exactly what we had before. And so just like the law says, the sum of all the voltage drops equal the source voltage. So the other thing that I want to show you is it's also referred to as a voltage drop because of this. So if I start here at my available battery voltage, I got 12.63. Then if I check and see what's available here to the first bulb, so this is power coming into my first bulb here, I have 12.62, 12.63. I'm losing a little bit by the time it gets to there, or it's right on the cusp. But then if I go and measure over here, then I only have 6 volts available. So where'd the other 6 volts go? The voltage dropped between here and here because it takes voltage to overcome the resistance of this bulb. So it used up about 6 volts of electrical pressure to push the current through that bulb to get it to here. Then, by the time it comes to here, the other 6 volts got used up, and I only have 0.009 of a volt left that pushes that current back. So we know that there was, 0.163 of an amp that was flowing in that circuit. So the amperage flowing in this circuit is the same everywhere. But I had about 0.163 of an amp, I think. 0.163. So I had amperage, about 0.163 of an amp flowing here. Then what this represents is because this conductor is in very good shape and it doesn't have a lot of resistance, it only took 0.009 of a volt to push the amperage from here to here. So that 163 milliamps, or 0.163 of an amp, took 0.009 of a volt to push those amps from there to there. Then because this load has all those windings of resistance inside that bulb, has high resistance, it took 6.413 volts to push that 0.163 of an amp from there to there. It took 6.2 volts to push that 0.163 of an amp from here to here. It took 0.008 of a volt to push that 0.163 of an amp from there back to the power source and complete that circuit or circle back to the battery. So the available voltage from the battery gets divided up based off of the resistance. So here's the other rule that I want you to remember. If something has a high voltage drop, it will have high resistance. So this has a very low voltage drop, so we can also say that it has low resistance, and we would want it to. It's a conductor. Conductors we want to allow electricity to flow easily, or amperage to move easily. And so that's a good voltage drop for this wire. And so then we expect high resistance from this. And so the voltage that this bulb is using is 6.413 of a volt. And so that represents that this has a high voltage drop, so it has high resistance. This one's using 6.2 of a volt, and so this bulb also has high resistance. This conductor on our ground side going back was only using 0.008 of a volt, so we can say that it has a low voltage drop and therefore it has low resistance. And so this is exactly how we would want this to play out. I also want you to notice that although these are two identical bulbs right here, they don't have the exact same voltage drop. This one has 6.43 and this has 6.02 of a volt. And so in this case, which one of these two bulbs, if I labeled them number 1 and number 2, all right, which bulb has higher resistance, bulb number 1 or bulb number 2? Even though they're identical, they don't have the exact same resistance. We know that this one has higher resistance. Bulb 1 has higher resistance than bulb 2 because bulb 1 has a higher voltage drop. If you have a high voltage drop, it will have high resistance. If you have a low voltage drop, it will have low resistance. So in this circuit, it plays out exactly how we would want it to. Our conductors, our power conductor in red and our ground conductor here in black from there to there, those two have very low voltage drops, and our loads are where all of that voltage is being used, which is what we want. Now, the other thing that I want you to notice is that in this series circuit, we started with 12 volts, and because we have nice, good conductors, then it basically split between the two. This one used about 6 volts, and this one used about 6 volts. That being said, if I added a third bulb to this, what do you think would happen? If I had a third identical bulb, if this one divided between the two, then how would it work with 3 bulbs? I'm going to go ahead and add my third bulb in. And then we can go ahead and look at what these bulbs are using. So, I want you to also notice that when I go from 2 bulbs to 3, the intensity also decreases, doesn't it? So, if I look at this circuit and the way that it's breaking up and dividing up this voltage, then if I look at how much this bulb is using, what do you think it's going to be? If you said 4 volts, then you're right. So each one of these bulbs now is going to use about 4 volts. Because 12 divided by 3 is 4 for these identical bulbs. So since their resistance is a little bit different, this one will be 4 and some change, and this one 4 and some change, and that one 4 and some change, but they all basically will divide up and get 4 volts. If I added a 4th bulb, then what are we going to get? We're going to get even dimmer lights. And now each one is going to run on about 3 volts. 2.4 some. 3.3. 3.4, 3.4. So as this guy warms up, he'll probably start stealing a little more. 2.4. But good enough. So as it warms up, then this one's voltage drop is going to increase just with like everybody else's. Now, one of the things to understand with series circuits is that these bulbs are dimmer because they're operating on now 3 volts-ish, right? They're a lot brighter when they're operating on 12 volts. So, and even 4 volts there. But you can see when this one operates on 12 volts, it's a lot brighter than when it operates on 4 volts. Or 6 volts, 4 volts, 3 volts, right? So they get dimmer as their available voltage to each bulb is less and less and less. So that also explains one of the scenarios that you have probably seen. But you've probably seen a car out there on the road that had one brake light that was bright and the other one was dim. You can notice right away that as long as those are the same bulbs and it doesn't have 2 different bulbs, then in all likelihood, one is operating on full system voltage, 12 volts, and the other one that's dimmer is probably operating on lesser voltage. So the explanation for that is that in most cases, they've got a bad connection causing a voltage drop. That if, for example, then I start out and I've got this bulb that's running on 12 volts right now, because I've got it all shorted out together. This one's on 12 volts. That if everything's fine and that's the way it's supposed to be, then it stays nice and bright. But if I have a circuit malfunction that then steals some of my voltage away, the thing is you don't get to see it. All you can see is that bulb is now dimmer than what it used to be. But we can detect that then with a voltage drop, can we not? I can say, well, hey, my power wire is using 6 volts. That shouldn't be, right? So it's using up 6 volts. And so then you can be able to detect stuff like that by using a voltage drop and using your voltage drop testing. So next thing that I want to cover is our last concept for our series circuit. So our last concept for our series circuit says the total resistance equals the sum of all the individual resistances. So what that basically means is that bulb right there has resistance, and so does this one. And so if I add this bulb to this circuit, the resistance will go up, so the amperage will go down. If I add another bulb to the circuit, and I add 2 in there, then the overall resistance, since this has resistance, this has resistance, this has resistance, then the overall resistance will increase. So the total resistance in a circuit is the resistance of this wire plus this bulb plus this wire, right? So I'm going to go ahead and set our meter up on amps, and then we're going to start adding bulbs into this circuit to illustrate that. So I'll switch it over to DC. We're going to clip in with our meter to measure amperage. So right now we're measuring the amperage for this one bulb, which is about 2.5 or a quarter of an amp, 0.253 of an amp. So 0.253 of an amp, which is a quarter of an amp. So the amperage is coming in through my red lead into the meter, out through the black lead, and on to the rest of the circuit. Now I'm going to go ahead and start adding bulbs. Now, to illustrate to you how predictable electricity becomes after you know a little bit about it, so I have 0.253 of an amp. This bulb has some resistance. If I add another bulb to this circuit, is the amperage going to go up or is it going to go down? So if I add a bulb to this circuit, the resistance of the circuit should increase, right? So if the resistance of the circuit increases, then the amperage, if resistance goes up, amperage will go down. So there's the second bulb. And we already know what's going on with this bulb, with these bulbs. This one's getting about 6 volts and this one's getting about 6 volts, and now the amperage went down to 0.166 or 65. So if I add another bulb to this, then the amperage again will go down as resistance increases. So now I'm down to 0.130 from 0.166. If I add another bulb to this, then I know the amperage will also go down even further. So now I'm down to 0.115. So as resistance increases, that proves the fact that amperage keeps going down proves that resistance is going up. So now to move on to our parallel circuit. So if we were going to hook up another bulb to this circuit, we know that if we take it apart and we put bulbs in this, that is series. For a parallel circuit, each bulb gets its own power and ground. So in this case, this bulb has its own power and ground, and then this bulb has its own power and ground. So I'm going to switch these around so that even though bulbs don't care, I'm going to hook my red lead to red and my black lead to black. Just for some of you anal people out there like me. So it doesn't bug you. So I got red to red and black to black, even though it doesn't matter for bulbs. Bulbs don't care about polarity. So each bulb gets its own power and ground. Our first rule for a parallel circuit is that the voltage is the same everywhere. Now conceptually that makes sense. All that really means is every bulb in this circuit gets its own power and its own ground. So they all get their own power and their own ground. So if we do look, that one, if I get my hand out of the way, I got 12.5455. This one also has 12.5455. So. Same nonsense. So I must have a little bad connection right here. So if I check this guy, I want it to make sure that you guys see the exact same. 1255, 1255. So each bulb has its own, they both have the same source voltage, all right? So then the next one is the total current is the sum of the current in each branch. This one I'm just going to explain to you conceptually because it's easy enough. There's one wire here. It's one wire all the way over here and it splits. The current that's flowing in this one single spot is the current for both bulbs. So the total current that's flowing is the current that's flowing in this bulb plus the current or amperage that's flowing in that bulb. The amperage for this one plus this one is the total current that's for the circuit that's flowing here. All right? The next one is the hard one, which it says the total resistance is always less than any individual resistance. So this one I'm going to demonstrate to you. So there's an individual resistance right now. So one individual bulb, and we'll get this guy back out. But if I go and I measure amps now, go back to DC amps. So if I measure amps for this circuit, and I get in here and measure the amps. So if I come and I get my amperage going for this first bulb. Since my law says for my parallel circuit that the total resistance is going to be less than any individual resistance, what in effect that means is that when I add another bulb to this circuit, the resistance of the circuit is going to go down. Now, I'm going to illustrate it. I'm at 0.248 of an amp right now. When I hook this other bulb in parallel, the amperage will go up like that to now 0.498 instead of 0.2, about 2.5, or sorry, a quarter of a volt. Now it went up to half a volt. If I add another one, the amperage is going to increase, illustrating that resistance decreased. So I'm up to 3/4 of an amp, 0.744. Now, the easiest way to understand this concept is simply this, that as I add bulbs in parallel, it's like adding lanes to a freeway. If I'm giving electricity more paths to flow, another path there, another path there, another path there, then that's like adding lanes to a freeway where now I can flow more cars. And so that's in effect what happens in a parallel circuit is you add paths, you add lanes to a freeway, and so now it can flow more cars on a freeway or flow more amps. And so in a parallel circuit, as I add bulbs in parallel, the resistance goes down and the amperage goes up. As you add bulbs in series, the resistance goes up and the amperage goes down. So this is our parallel circuit. As you add bulbs in parallel, the resistance then goes down in parallel. So that's our laws for series and parallel circuits. There is something called a series parallel circuit. So in case you were wondering, there is something called a series parallel circuit, and I'll just show you one real quick. So this is parallel right there, and then if I add this bulb in series. Like that. I'm going to do it to the... That doesn't matter. All right. So you don't see these a lot. They do it sometimes for cooling fans, which we'll talk about in our electrical class if you take it with me. Another application for this is a high beam indicator. So as this is wired up right now, this would be the circuit for the high beam indicator, and these would be the low beams. All right. And so the high beam indicator would come on, and we would backfeed power, which you can see these are dimly lit on those bulbs, but this one's nice and bright. That would be what it would look like when the high beams are on. When the low beams are on, what they do to this low beam indicator is then and this would represent our low beam circuit there. This, when they switch to off of high beam, then what they do is they then connect that like that. That makes this have ground and ground. The high beam indicator goes out, and then the low beams come on. And there would be separate wiring for the high beams. And so that would be an example of what they do on cars for a series parallel circuit. So right now, this one bulb is in series with these two bulbs that are in parallel. So don't get nutted up over it. You could fix that car. If that high beam indicator didn't work, you could fix it and never know it's a high beam indicator. For example, at your house, when a bulb goes out, right, and it quits working, you get the meter out, right, and you start checking to see if there's power to it and all that kind of stuff, right? Oh, I better see how many amps are flowing, and I better check the power to it. No, nobody freaking does that. And we don't do that in the automotive industry either. When bulbs don't work, first thing we're going to try is what? Same thing you do at your house, another bulb. So if this high beam indicator did not work, right, then you grabbed another bulb and you slammed a bulb in it, and then it started working, you could fix that circuit and never know that there was ever a problem with that, or never know that was a series parallel circuit. So I don't want you to get too nutted up. Keep it simple in automotive. That's what we're going to do, is just keep everything simple.